We're going to do sections 4.3 and 4.4. Next class, we're going to do 4.7. The following class, we'll do like a, just some like practice in class on related rates that I think we're still probably not feeling very comfortable about. These derivative tests that we're going to talk about today, and then optimization, that'll be what we'll talk about next class. That'll probably be it topic-wise for the semester. So we just have remaining will be the homeworks from those sections. So 3 homework pages or whatever. Yeah, no.
These are the finals will look somewhat similar to the tests that we've had.
So we'll talk about that here in a moment. Is everybody okay with that plan? I'm not gonna do any more homework quizzes because quite frankly, it's just like trying to get through the material here to get us a little bit more caught up than we were a little behind at one point when we had this conversation, I think. So that's it. There's just like, I think 2 homework assignments left because I think I'm grouping 4.3 and 4.4 together. And 4.7 is the last one. Friday next week will be the last day for any later missing works. Okay? So if you have lates and missings or whatever, and you still planning on completing those, make that a priority more sooner than later. Noah is asking about exam credit, or exam format, excuse me. Oh, it's just like, think difficult here. Maybe just the word is difficult.
Yeah, I think you have the worst luck with technology ever.
It feels that way today.
Especially in our IBSL class.
All right. All right. So this is the same format I used last year. Now I haven't gone back and done any editing to the exam based on what we covered this year versus last year and any other adjustments I might want to make. But I think the format will remain the same. So your exam is going to be graded out of 50 points. There's a total of 86.5 points on the exam in total. That number may shift a little depending on edits that I make, but way more points than you need for 100%. The exam will be divided into 5 sections. So you're going to have multiple choice questions, limit questions, derivative questions, like definition theorem questions, and application questions. Each section is going to contain between 10 and 20 total points worth of problems. Your goal is to get 10 points per section. So you can do more than 10 points worth of problems, and any kind of partial credits may add up to 10 for you. But you can't carry extra points earned in one section into the next section. So if you got 12 out of 10 in the first section and 7 out of 10 in the second section, you still have 17 out of 20. Like the extra 2 points from section 1 doesn't carry through and count as like extra credit or something, just inside of section 1. Does that make sense to you guys in terms of format?
Yeah.
So it's open calculator throughout. It's all one section. You go back and forth and forward and back and can return to early parts of the test at the end. You can do it in any order you like, but that's essentially the format. The types of questions that'll live there, that's got to get updated. The total amount of points in each section, as I edit questions, may change a little bit, but that, that format I think is, a pretty fair one at this point. Gives you some freedom to avoid things that are like, oof, what the heck do I do with this? Or like, well, I look at that and that looks like a nightmare. Like it's like I think I know what to do, but it's going to take a long time. You can skip it and try something else. It allows you a little bit more to focus on the things that you just show me that you really feel good about, that you know how to do. And avoid the things maybe you're weakest at, to some extent anyways. Does that feel like an okay format? And again, I tried to group this into like the main things that we did this year, right? So the most of this semester has been, can you do a limit? Can you find a derivative, right? And now we're doing, can you do an application of, like, what do these derivatives allow us to do, right? I have some definition and theorem stuff, because that's still important. I have some MCQ stuff, because we spent a lot of time practicing. Those have been a part of every test. I think that's important to continue. Mark?
Other than related rates, what would the application section have?
So optimization, which we still need to talk about. These first and second derivative tests that we're going to talk about today, I think are all good candidates for an application problems. Does that feel okay?
Fuck the theorem problems.
So like things that we've used, like the squeeze theorem to do, or the intermediate value theorem, or the mean value theorem, or like problems. We've had a bunch of these theorems and definitions, or like showing a function is continuous or not, or differentiable or not. Like we've done a lot of practice of things like that, on definitions and theorems. I think that would be the kind of problem that would live there, where it's like a little bit more open-ended, where it's like you have to show something rather than just like find the derivative of this thing. Does that make sense?
Yeah.
Sure. And that should feel pretty representative of like what we've spent most of our time doing this semester is like this stuff. Okay? And we can talk more about like finer grain details, but that's an overview of like what it's gonna look like. So you need to be pretty prepared, but if you feel weak in a couple of areas, it's probably okay where you can avoid, might be able to avoid that particular topic, but you can't be bad at both related rates and optimization, because you're gonna have to do probably one or the other to get your points in the application section. So you can be like, yeah, I'm gonna,
So basically, we're gonna have multiple questions in each section.
you have way more points than you need to get 100% for that section.
Okay, so then whatever, like, we feel comfortable doing, we're just.
You can do as much, you can do all the problems if you have time.
Mhm.
Not my recommendation. I would do the minimum, the first pass through, and then come back and be like, I felt terrible about this section, let me do some more in here and try to squeeze out some more points.
Okay.
But, and again, I leave that up to you.
Will it
in
tell
terms
us
of
how
your
many
time
points we're
management.
getting in each question?
Well, from the
okay.
section, all the questions in the section are the same value.
Okay.
So it's literally like, that's it. So they're all valued the same way, so you can pick and choose. Does that make sense?
Mhm.
Again, I tried to make this simple but like flexible, right? Sound good? Okay. So let's dive into these last couple of sections here.
So like,
Oh,
sorry, real
that's
quick.
okay.
Hypothetically, if someone were able to answer correctly all 86.5 points, their grade would be 173%.
Remember, you're capped at 10 points in a section,
Oh, okay.
right? You don't carry points from one section, extra points into the total.
Okay.
If you get 12 out of 10 in a section, you just have 10 points in that section.
Okay.
It's just
Never
a full
mind.
10.
Thank you.
So yes, I mean, good luck. God bless you. If you could do it, that'd be something. I'd be really proud of you.
Thank you.
You don't need to do that though. Like 10 points in a section is good. So the easiest section to get the 10 points in should be
MC.
the multiple choice, because you can just like guess at stuff and have chances of picking up free points on stuff you don't need. It's like, why would you not answer every question? Even if it's just like, we got a minute left, let me fill in circle some letters here. All right. In section 4.3, we're going to continue talking about what can the derivative tell us about our function. And we started this a little bit in 4.2 and 4.1 even, where we talked about like finding absolute maxima and minima, right? When can we absolutely find absolute minima and maxima? Guys, on a closed interval for a continuous function, the extreme value theorem guarantees us that we have a local minimum, a absolute minimum and absolute maximum. Need not be unique, they may be more than one, but it guarantees us that we have those things. If you have an open interval, not so easy. There you have to look at the limits. Even if you have continuity, if you have an open interval, then you have to look at the limit of the endpoints. It can be tough, potentially, depending on what the function is. All right, although slightly easier today after we do section 4.4. Okay, so today what we're going to do is talk about how we can identify local extrema. That's going to be one of the main ideas in section 4.3. Okay, so local mins and maxes, how can we identify that? Because even if I use my critical values like we talked about in 4.1 and evaluate those critical values, I still have no idea if that number is a local minimum or maximum if the one is bigger than the other. I can tell the absolutes on a closed interval, but anything that's not an absolute min or max, I have no idea if it's a min or a max. And if it's not a closed interval, I don't know what to do with that. So that we're going to talk about that here today. So we're going to start here just talking about some basic ideas, or review a basic idea, that when the derivative is positive, that means the function is increasing, that f is increasing. And when the derivative is negative, that means that the function f is decreasing, right? Positive slope, negative slope. Everybody remember this from way back at the very beginning? So let's do a quick example here. I'm not going to bother to prove this because, like, no thank you. Let's take the function here, 3x to the fourth minus 4x cubed minus 12x squared plus 5, and find where it's increasing and decreasing at. Sound good? To do that, what should I do first?
Take the derivative.
Find the derivative.
We're masters of that.
Yeah, and this is something that you should be real comfortable doing. Okay. What do I do next? Where can this derivative change sign? Because I need to know where it's positive and where it's negative. So where can it change sign?
Make it equal to 0.
When it equals 0 or where else?
Where x is positive or negative. Because then that would mean no.
Where there's a discontinuity. What are those two things called if I look at the place where the derivative is equal to 0 or where it doesn't exist? Those are called the critical values. Okay. Now, one of these two is really easy, right? Which one can I do quickly just by inspection? This guy. What type of function is the derivative? Polynomial. What's the domain of a polynomial? All real numbers. Is the derivative going to fail to exist anywhere? No, because its domain is all real numbers, right? Nothing to do there. None. Everybody good? Okay. If I want to do the derivative equal to 0, how do I solve 12x cubed minus 12x squared minus 24x equal to 0?
Set that equal to 0.
Factor what? 12x first. Yep, so we're setting it equal to 0, and then we factor out a 12x. Oops, I don't need a 1 there. Okay. Then what should I do?
Divide by 12x, so that just goes.
Ooh, no. You can't divide by a variable. What if that variable is equal to 0?
Oh no, make them both equal to 0.
Let's factor again, right? There's a quadratic there. How does x squared minus x minus 2 factor? Good. And that should be fast and instant for you guys. You should be able to do those in your head. If that's not the case, you've got some catching up to do, but that should be something that's a mastery level skill like 2 classes ago. You should be very good at that. Just communicating, not threatening, just communicating. And from here, yes, we set each piece equal to 0, And our solutions would be 0 to a negative 1. Everybody good? And again, you should be able to do that in your head. Should be no problem. You don't need to show that work. If you have the factored form, you can write down the answers. That's fine. Okay? So far, so good? So to figure out where this function is positive and negative then, let's make a sign diagram. Do you remember doing this in pre-calculus to solve like inequalities? Okay? We'll pick a test value from each of these intervals then. Is there anything magic about the test values I chose here?
Oh, they're all.
No, as long as they live in that interval, it doesn't matter, right? Now, where am I going to plug these test values in? To f or f prime? F prime, because we want to know where the function is increasing and decreasing. That, the derivative tells me that, right? Now, when I plug those into f prime, do I care what the number is? I just care about the sign, right? So when I plug these in, am I going to bother computing out what the actual number is? What am I going to do? Just worry about positive or negative. So when I do that, I'm going to use the factored form. So if I plug negative 2 in, I have a negative times a negative times a negative. Everybody agree? 12 times negative 2 is negative. Negative 2 minus 2 is negative. Negative 2 plus 1 is negative. 3 negatives multiplied together makes a negative. Yes, sir.
How do you know that, like, why are you plugging into the derivative function and not the original function if it's asking if it's like increasing and decreasing?
Because this being positive or negative isn't telling me anything about it being increasing or decreasing, right?
Oh.
Right, like if f is doing this, it's increasing there, but the value is negative,
Okay, no.
right? I don't care about that. I care about what the slope is. Derivative tells me slope.
Thank you.
All right, let's do the negative 1/2 now. So negative, negative, positive.
Positive.
Everybody agree? Notice that this could still be a no calculator problem, right? The way I'm attacking this is the way you'd want to attack the no calculator version of this. We do not need the actual numeric values for f prime. Now you could calculate them by hand. It's going to take some time though. How fast is this, what we're doing? In a time test, the fast student wins, right? You get more time to work on stuff that's really hard rather than stuff that's tedious. If you can find a quick way through the tedious stuff. All right, we plug 1 in, positive, negative, positive. And if I plug 3 in, they're all positives. But you look at it, you can see it. Okay. So we would say f is increasing from negative infinity to negative 1. And then, I should say decreasing. And then from 1 to 2. And we can say f is increasing from negative 1 to 0, or from 2 to positive infinity. Sarah?
With the second one, it's increasing be 0 to 2.
Oh, yes, thank you. Of course. Yes, thank you.
Yeah, I was just making sure it wasn't the number, like you didn't put the number.
Yeah,
They
no,
put
you,
Okay.
it's a good catch. It's 100%, yes. I made an oopsie. Look how easy it was. It's good to see it, right? Everybody feel great? Easy peasy, right? In terms of things we've been doing, the calculus parts, very easy. Some pre-calculus stuff afterwards, but not bad, right? First derivative test. So the first derivative test is going to allow us to locate local maxima and minima. So what the first derivative test says is that suppose C is a critical number of a continuous function f. So you need continuity to do this. If f prime changes from positive to negative, then that value C is a local maximum, which again, if f prime is positive, it's increasing. If it changes to negative, decreasing, what's that look like? A maximum. If f prime changes from negative to positive, so decreasing to increasing, we should have a local minimum. And if it doesn't change, if it goes from increasing to increasing, or decreasing to decreasing, we don't have any extrema there. Does everybody feel good? And this picture's illustrating the same thing, right? So, do you need to memorize this? I don't think this needs to be verbatim, you just need to know it when you see it, right? Like, if you can remember how to draw the picture, you know whether it's a max or a min, and that's really all you need. Does that feel good? Okay. And again, you could have probably cooked this up by yourself, but yeah. All right, so it says, go back to example 1 and find the local maxima or minima and maxima for the function. All right. So those are our 3 candidates, correct? Decreasing to increasing, that is a local minimum. Get used to putting the word local in there. Increasing, to decreasing, maximum. And then decreasing to increasing, minimum. So if this same question asked for, I find the local minima and maxima, we do the exact same process that we did to find the intervals of increasing and decreasing. We just have the additional step of looking at how the signs change from increasing to decreasing to identify the minima and maxima. Everybody's good? Okay. Let's do another example. Trig time. Find the local minima and maxima for the function g of x equals x plus 2 sine x on the interval from 0 to 2 pi. We should start by finding the derivative. What is the derivative of g of x?
2 plus 2 cosine x.
Good. Okay. Everybody feel good there? Then what do we do?
So it equals 0.
And,
Direct does not exist.
good. I always like to do this part first. Where does 1 plus 2 cosine x become undefined? Mark, what's your answer there? Never. Good. Why?
Because it's just a little squiggly, like forever.
Yeah. 1 is a polynomial. Domain is all real numbers. Cosine, domain is all real numbers. 2 things, continuous things with all real numbers. You add them together, you still get all real numbers domain. So, lovely. None.
Would that be the same if it was sine?
Yes. Would it be the same if it was tangent? No.
How
What
would
if-
you figure that out then?
You have to remember a lot about trigonometry.
Will we be asked that?
Possibly. The same would go for like secant or cosecant or cotangent. Right? Those are all have discontinuity.
Okay.
For if it was tangent, tangent is sine over cosine. So I would need to worry about where cosine is 0, which happens at pi over 2 and 3 pi over 2. I know. I know. But at one point, we knew these things.
At one point.
Yeah.
Not very well.
I know. Don't worry, because it's about to come back.
Yeah.
All right. So if we want to solve 1 plus 2 cosine x equal to 0, what do we do? 1 plus 2 cosine x equal to 0.
Subtract 1.
And then?
Divide by 2.
And then?
Inverse.
Cosine inverse, right.
Wait, hold on.
Yes? Or am I still holding?
No, it's.
Okay. Perfect. All right. Trig master. Where is cosine negative? What quadrants? 2 and 3. Everybody agree? The left side of the unit circle, because which coordinate is cosine?
X
X. Where is x negative?
on the left side.
On the left side of the unit circle. Okay? So we're looking for answers in 2 and 3. Everybody agree? When I see a sine or cosine value of 1/2 or square root 3 over 2, I know that the angle, I should say the reference angle, is either a 30 or a 60. Everybody agree? So if I think about a 30, the short side is the y side and the long side is the x side, right? If I think about a 60, the short side is the x side and the long side is the y side. Everybody agree? So 1/2 root 3 over 2. Which one is the short, which one's the long? Let me give you a favor. Decimal approximations for your trig functions. Sine, 1/2, 0.5.
5 over 2 is 1 over.
Root 2 over 2,
Over 2.
0.707. Root 3 over 2, 0.866. Those are numbers you should remember. Those help a lot, just remembering those decimals. The pair with 1/2 is 0.866, correct? We want the 60-degree reference angle. Everybody agree? In radians, what's 60 degrees? Pi over 3. In the second quadrant, what angle has a pi over 3 reference angle?
2 pi.
2 pi over 3. Very good. So that's one of our answers. And in quadrant 3, what angle has a
4 pi over 3.
4 pi over 3?
It's like you memorize the first quadrant, the second is a little bit under, then over, then almost double.
Yeah. So again, I didn't remember 2 pi over 3 and 4 pi over 3 automatically, right? I drew myself a picture and worked it out because I forgot the memorization, but I'm not sunk because I remembered stuff, right? Like I knew which was the other coordinate that had to go with the 1/2, and I knew that 1/2 was less than the other one, and I knew it had to be either 30 or 60 as the reference angle. I was able to work it out from there, right? Even if you don't remember the unit circle, where you're just like cranking them out, I did that and I could have done it in under 30 seconds. You know, it's not a huge time suck, okay? Just to show you what you can do if you don't remember. That's the way I would go about doing this. All right, I'm gonna erase these pictures here because they aren't exactly germane to what we're trying to do now. So we have 2 critical values, correct? We also have endpoints. Okay. Everybody's good? How many test values do I need?
5.
3. I don't need anything less than 0 or anything greater than 2 pi. Why?
Because the interval ends.
The interval ends at 0 and 2 pi. Oh, great. So I just need a spot a test value here, here, and here. Yes? Okay, what value should I pick between 0 and 2 pi?
0.5.
How about pi over 2? That would be my choice. Why would I pick pi over 2?
Something in a circle.
It's a quadrantal angle.
So what?
It lies on a quadrant on one of the axes, right? Those are my favorite ones to use because they're really easy to compute.
Okay.
Like I want quadrantals. I know, it's a funny word to say. Between 2 pi and 4 pi, which I pick?
3 pi.
Pi!
Pi.
Yeah.
Okay.
And between 4 pi over 3 and 2 pi?
Pi. No.
3 pi over 2.
3 pi over 2, yes. Okay. So, plugging in here, what's cosine of pi over 2?
0.
0. 1 plus 0 is?
1.
Oh, positive for us. That's all we care about. But 1 is also acceptable.
Yeah.
What's cosine of pi?
-1.
-1. So this is
Negative.
negative. Okay. And then cosine of 3 pi over 2?
1. 0.
0. So this is positive. So what do we have here? Local max and local min. Everybody feel okay? What was the hardest part?
Trig.
Doing the trig solving, right? It was probably the trig solving, the calculus. Pretty easy. The hard part was coming up with 2 pi over 3 and 4 pi over 3 and then picking, well, doing a good job of picking our test values, right? First period, someone's like 1 between 0 and 2 pi. I'm like, 1's an insane answer. Who the heck knows what cosine of 1 radian is? No idea. No idea. The crazy answer somebody gave me. I don't remember who it was because I would tell you just so we could all have a good chuckle about that answer. I was like, what? That is an answer there.
Should have told him I want a rectangle angle.
Yeah, quadrantal.
Yeah.
I did say that word then, and everyone's like, huh?
Yeah.
Is that terminology? All right. Let's talk about second derivative now. So first derivative tells us increasing and decreasing for function, right? The second derivative is going to tell us how the function is bending. So the concavity, whether it's concave up, so it's like bending up, or concave down, like bending down. So I think concave up sounds like cup. So the curve should look like a cup, like it's filling water. If you dumped water in the curve, it would hold it. Concave down, should water run off.
You don't have a word for
I
it?
don't have a word for
Okay.
that.
It was only too hot.
Yeah, I mean, it's just not cup.
Okay.
Down, not cup. So this is an example, concave up, concave down. Let's take a look here at this function. So we have 1, 2, 3, 4, 5, 6 intervals mapped out here. We're just going to decide whether we're concave up or down on these 6 intervals. So from A to B, up or down? Down. From B to C? C to D?
Down.
D to E?
Up.
E to P?
Up.
P to Q?
Down.
Okay. So these places where the graph changes concavity, these have a special name. They're called an inflection point, where the graph changes from concave up to concave down. I think I have that written down later also. So if I want to check for the concavity of a function, all I'm going to do is check where the second derivative is positive or negative. Would this change materially for where I check for how I check for the function increasing or decreasing? It's the exact same process except I'm using the second derivative instead of the first. if it's a polynomial, does that make the problem easier or harder?
Easier.
Easier, because a polynomial gets a lesser degree every time you differentiate, so the solving becomes that much simpler. We like that. I'm skipping this example. Here's my inflection point definition that I knew was coming. I just kind of jumped the gun on it a little bit, I guess. So a point P on the curve, y equals f of x, is called an inflection point if f is continuous there and the curve changes from concave up to concave down, or from concave down to concave up. All right. Next example asks us to sketch a possible picture of the curve from some information. So we're told that the first derivative is positive from negative infinity to 1, and then the first derivative is negative from 1 to positive infinity. The second derivative is positive from negative infinity to negative 2, and also from 2 to positive infinity. And the second derivative is negative from negative 2 to positive 2. And the limit as x approaches negative infinity of f of x is equal to negative 2. And as x approaches positive infinity, the limit is 0. Everybody okay with what we're given here? So it doesn't really matter which order you want to attack these attributes in. Me, I'm going to start with the stuff about f directly first. Is that okay? That's just what I like to do. So if I'm given information about like x-intercepts or y-intercepts, I'm going to do those first. Or if I'm given information about the limits, I'm going to do that first. If I look at that statement, those limits there, what are those limits telling me? You can use pre-calculus language or calculus language. I'll accept either answer. What are those limits there in part 3 telling me?
Does it say as x is approaching negative infinity and infinity?
Positive infinity, yes, 100%, yes, good eyes. What's that?
The asymptote,
Ah, what kind?
horizontal.
Yes, in the parlance of calculus, that is our definition for a horizontal asymptote. In pre-calculus, you would call this your end behavior, would have been the verb you would have used there. Okay, so let's draw those in. So here's the horizontal asymptote at y equals negative 2. Here's the horizontal asymptote at y equals 0. Everybody agree? The left end of the graph is going to be doing that. We don't know which side of it should be on, so I'm going to draw both sides and then erase. And this one should be, kind of doing that, right? Again, I don't know which side it's going to be on. I'm going to draw it on both and then just erase. So far, so good? Okay. Then I'm going to go to the first derivative next. So here it says that I'm increasing to 1, and then I change to be decreasing at 1. What does that tell me happens at 1?
Switch local line.
Say local maximum, right? So I'm going to draw that somewhere. I don't know, I'll put it here. Does it matter where I put it? Probably not. I wouldn't want to put it below here, though, I don't think. I would want to probably put it above my horizontal asymptote. I think that's probably, I don't think anybody would be crazy enough to try to put it down there. Everybody's okay? All right. So I know this has to connect there, and then it has to connect down. And then if I look at this guy, what is this telling me? Well, all the way to negative 2, we should be concave up. Oops, let's make negative 2 there. And then it changes to positive 2, where it should be concave down. And then at positive 2, should change back to concave up. Does everybody kind of see how I kind of connected that all together? So this part and this part I didn't need, so I'll erase those. And that's a reasonable sketch of my curve. Okay, notice that there's no y-coordinates given because I'm not plotting anything, I'm just sketching. That's going to be ish the shape. Could it have varied wildly in what it looked like? Oh yeah. I mean, you could have like, you know, all kinds of weird looking things, but it's okay. Ideally, I would have like put a little spot here and maybe labeled them as like inflection points and like local max and stuff to just, if I'm doing this on an AP exam, just so that they know when they're looking at it that that's what I'm trying to draw. Maybe my art skills aren't that great, which is where I live. Substandard art skills. Do we feel okay about this idea though? Relatively easy, right? If you know what you're looking at. And again, my suggestion to you is that you approach it in this kind of an order. Do the stuff pertaining to f, do the stuff pertaining to the first derivative, to second derivative, and just kind of like piece it together. It's a little bit like a Sudoku puzzle or whatever. I do too. Second derivative test. This does the exact same thing as the first derivative test. Just identifies local minima and local maxima, just using a different tool. So it says that suppose the second derivative is continuous near the critical value c. If the first derivative is equal to 0, and the second derivative is positive, that's going to be a local minimum. And if the first derivative is 0 and the second derivative is negative, that'll be a local maximum. The advantage of the second derivative test is I only have to plug one thing in instead of two. Right? In the first derivative test, I have to do a test value on either side of c. Right? I have to plug two numbers in. In the second derivative test, I only have to plug one number in. I just have to plug c into the second derivative. So again, either is fine. They do the exact same thing. The majority of the problems you guys will see either can be used with this equal amounts of effectiveness. On some very rare occasions, one of them would be possible and the other wouldn't, but that would be a result of just like you're not given enough information to do the other one. So like if you're given just, here's a function of f of x, and here's some table of information about f, f prime, and f double prime, where you can't plug in test values, you can only use what you're given. Probably a second derivative test is all you can do there. Or if you're given an implicitly defined function, typically you'd want to go with a second derivative test there. It makes it massively easier than a first derivative test. We could talk about that later if you really were interested in it, but just take my word for it. All right. So it says, discuss the curve y equals x to the fourth minus 4x cubed with respect to concavity, points of inflection, and local maxima and minima. Use this information to sketch the curve. I'm not going to do the curve sketch after I'm done. Is everybody okay? Okay. If I want concavity, what am I going to need? Second derivative, right? What do I start with, though?
First derivative.
Okay, and which is?
4x to the third minus 12x squared.
Great. And so the second derivative then is?
12x squared plus 24.
Okay. And to find the concavity, what do I need to do? Or does not exist. Let's do the does not exist piece first. What's the solution to that? None. Why?
It's a polynomial.
It's a polynomial. Good. To solve this equal to 0, what do I do first?
Take out the values.
Okay. So my solution should be,
0 and 2.
okay. Since I potentially am going to do more than one sign diagram here, I'm going to put F double prime by it so I remember what I'm doing here. Okay. So those will be the test values I pick. When I plug -1 into here, I get positive, right? Negative times negative. When I plug 1 in, I get positive times negative, so negative. And when I plug 3 in, I get positive times positive, positive. Is everybody okay? So for concavity, so where are we concave up at? Negative infinity to 0, or 2 to positive infinity, right?
Yeah.
Where we concave down at? 0 to 2.
Is this the concaveness of
F.
double prime or just F?
F.
Okay, cool.
Okay? Points of inflection. What are the inflection points? What does that mean again? Where we change what? Concavity. What values of x does that happen at?
0 and 2.
0 and 2. Everybody feel good there? Okay. The last thing I want are local maximum and minimum. What do I need to do that? First derivative set equal to 0 or does not exist. Obviously, there's no solutions to that because, again, it was a polynomial. What are the solutions to the first derivative set equal to 0? Okay. So far, so good. You know what I'm going to do? I'm going to do a second derivative test here. You know why? Because I already know that f double prime of 3 is greater than 0. Look, I already did it. I didn't even mean to do it, and I did it. Oh, that's so nice. What does that tell me then? Is it a maximum or minimum?
Wait.
Because it's concave.
So concave up.
Oh, there's no
Oh,
local min or
minimum.
max
Minimum.
at
Yeah.
0.
So I have a local maximum at x equals 3. Do I have enough information currently to make any conclusion about 0?
Isn't there no local min or max? Because it goes from, oh no, positive and negative, so it would be,
We don't know yet, right?
okay.
Everybody agree? Now, oh, I see what you're saying, Brooks, yes. So we also know that, yeah, so you're right. F double prime of 0 is equal to 0, right? So that tells me this guy is nothing. Because again, we had that second derivative evaluated already for us. So again, here's a case where, could you have done a first derivative test instead? Yeah, but you already did all the work for the second derivative test in doing the other parts of the problem. So like, why not just do that one? Save yourself a minute. But if you didn't notice that, would you have gotten it wrong if you did the first derivative test? No, you just would have spent a little bit extra time that you didn't need to spend. You feel okay on this? This should usually feels pretty good, right? What's the hardest part here? Just keeping track that you're plugging things into the right layer, right? Am I going into the first F prime or F double prime, making sure I'm plugging things in the right places. But if you can keep that straight, it's usually fairly easy because the algebra and the calculus are not difficult. Okay, just making sure you're on top of where you're at. 4-4, back to limits, return to limits. No! What was the hardest thing what was the hardest kind of problem when we ran into limits? When you got an indeterminate form and you had to do like some sneaky crap to get around that? Guess what? This is now the sneaky crap to get around it. It's the same every single time. Oh, splendid! So remember, we had 7 indeterminate forms, 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. Those are the 7 indeterminate forms. Any one of those tells you nothing about your limit after direct substitution. L'Hopital's rule states, suppose f and g are differentiable, and the first derivative of g is not 0, on some open interval that contains a, except possibly at a, and suppose that the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0, or that those limits are positive or negative infinity. Then, the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. So if you have an indeterminate form, either 0 over 0 or infinity over infinity, instead of doing any algebra, we just take the derivative of the top and the derivative of the bottom and try another direct substitution. And if it works and we get an answer, we're done. If it doesn't work and we get another indeterminate form, guess what we do? Just differentiate again. And we can keep doing that until we get something that's an answer trickles out. Or on rare occasions, maybe there was some simplification thing we had to do because it's like we're getting further away from it settling down. Let's look at some examples. Of course, yeah.
Strictly,
Yes, sir.
so is it only on those 2 indeterminate forms?
Yes, if you have a different indeterminate form, what we have to do is do some algebra to smash it into one of the other indeterminate forms, or into the fraction indeterminate form, so we can use L'Hopital on it. But that's it. Still, the idea is like, okay, like we just force it into the hole, and then we hit it with the hammer, right? We just make it work, so we can do this thing to it again. So, I wouldn't expect, like I have examples in here of all the different indeterminate forms. I've done a lot of practice AP questions. I don't see anything that's not the 0 over 0, infinity over infinity making it on there. You should be able to do a 0 times infinity though pretty easily just by making a reciprocal, multiplying by a reciprocal, and that'll get you what you need into an indeterminate form. It's like, oh yeah, like if I have like 1 over x times, cosine x. Right, 1 over x is infinity, cosine x is 0. What would I do? Well, what if I just turn that into like, instead of cosine, or instead of 1 over x, why don't I just make that x? Well, no, I just make one of them the reciprocal, right? Or I'm sorry, I'll turn cosine into like secant or something, and just like multiplying, you know, like I do 1 over secant or something, and then I just can make it into a fraction or something, you know. Anyway, continuing on. So here, all limit problems, we start with the direct substitution. So if I plug 1 in, I have this. Natural log of 1 is?
E.
No,
1.
0. 1 minus 1 is? 0. What do I have? Indeterminate form. What do we now do? L'Hopital's rule. The typical notation is when you apply L'Hopital's rule, you write your equal sign after the limit, you put LH over top of it, indicate that you're doing L'Hopital's rule. And here's the best part, or another great part about L'Hopital's rule. It's the derivative of the top over the derivative of the bottom. Do I ever have to do a quotient rule here? No, it just keeps getting better, doesn't it? What's the derivative of the natural log of x? 1 over x. What's the derivative of x minus 1? 1. So if I do a direct substitution now, what do I have? Oh, done. How would have you had to do that before?
Like do the whole entire like.
I think a squeeze theorem is what you would have had to do. I don't think that like multiplying by 1 over x is going to get you there. Like that's a squeeze theorem. That stinks.
Which one was that again?
You have to find an upper and lower bound for the function, and then you do the limits of the upper and lower bound. And if those limits are the same, then the thing in between is the same. Yeah.
Can we do this on a test?
Yes! Yes! Great question, yeah. So on the test where I ask you to like take the derivative of something or take the limit of something, you can use any tool to do that. Frankie's like,
Yeah.
those limit problems just got a lot easier for me. All right, let's do another one. Limit as x approaches infinity of e to the x over x squared. We always start direct substitution. What's e to the infinity? Infinity. What's it, infinity squared?
Very large.
Infinity, right? Everybody agree? What is this? Indeterminate. What do I do with an indeterminate? L'Hopital. The hospital.
Oh, that's what I thought it was when I first saw it. That's weird.
That's the name of the mathematician that came up with this. L'Hopital. Not the hospital. I know. You really want it to be though, right? Call the ambulance. All right. The derivative of e to the x is? The derivative of x squared is?
2x.
Okay. We do another direct substitution. We get infinity over infinity again. All rats. What do I do?
Do it again.
Do it again. Hit it again with the hammer. Just keep pounding away at it until it fits. What do we know now? It's immediately, it's not indeterminate, right? Because we have a constant on the denominator. We're done. Who likes this? Is this not like really nice? It's like really nice.
Who started with that?
Well, the problem is we don't know how to do a derivative, right?
Yeah.
We had to know how to do derivatives before we could do this. And we had to know what a limit was to define a derivative, right? It's a vicious circle.
Yeah.
All right. Direct substitution. Natural log of infinity is? Infinity, yeah. How do you know that?
Because it just infinity gets larger and larger.
So if you look at the graph of the natural log of x, it looks like this, right? What's happening to y? As you go to the right, infinity it goes. Not very fast, but it's going there. What's the cube root of infinity? Infinity. How do I know that? right? That's the graph of the cube root of x. What's happening to y as we go to the right? Infinity! Is it getting there very fast? No, not really. But fast enough. We got an indeterminate. What do? We hit it with the hammer. What's the derivative of the cube root of x?
3x to the 2/3, or negative 2/3.
Third x.
Do you see it or no? Right, the cube root of x is, oh, come on. Yeah. So it comes down, subtract 1. All right. What do we do now? Okay. What's going to happen now? What's 1 over infinity? What's 1 over infinity? 0. Thank you. Right? So think about it. You have a 1 on top, denominator getting very big. 1/2, 0.5, 1/3, 0.3 repeating, 1/4, 0.25, 1/5, 0.2. Where are we heading? 0. Right, got it? This 1/3 times infinity to the negative 2/3 is?
Really getting bigger? Or no, getting smaller too.
0.
That's indeterminate too.
Why?
Because 0 is on the bottom.
Because you have x in the denominator, yeah. Because the negative exponent. Okay, what do?
Derivatives.
Hit it again, right? You'd think that. Okay, what are we going to get here? We get negative x to the second over negative 2/9 x to the negative, 8 5/3. If we do another direct substitution, what are we going to get? 0 over 0. What do you notice that's happening here? Are those x's getting out of the denominator? No. If we keep hitting this with the hammer, what's going to happen? The exponents in the denominator are just going to keep getting bigger on our x's, right? At this point, I would stop because I don't like where this is heading. I'm going the wrong direction. I'm getting more indeterminate. Where was I the least indeterminate at? Back at this step. What could I do here instead of hitting with the hammer?
Do it the old-fashioned way, and whatever that was.
Well, what do you notice about the terms in the numerator and the terms in the denominator? They're like terms, aren't they? They're just x's to some power. What if we combine the like terms here? Before we decide to hit it with a hammer again. Maybe we didn't even need to hit it with a hammer here. So in top, I really have x to the negative 1, right? What do I get when I do x to the negative 1 divided by x to the negative 2?
It's like negative 1 minus 2, negative 2/3.
Mm-hmm. So I get x to the negative 1/3, right?
Sure.
Very good. Do I need to L'Hopital this? Is this indeterminate? No, man. What's this going to be if I direct substitute this?
0.
Done. So, we need to add one little step to our list here, right? After we L'Hopital, check to see if we can combine like terms. If we can combine like terms, do that, and then direct substitute. If they can't combine like terms, like something like this, just hit it again. But we should check to see if we can combine like terms before we hit it with the hammer one more time. Because we might have what we already need, right? If you keep hitting it with the hammer, L'Hopital hammer, when you don't need to, just things keep getting worse and worse and worse. What do you guys say here? You want to do one more, or do you think you get the idea? Should we do one more?
Or just for the heck of it?
One more for the heck of it? I love your attitude. I'm going to pick this one because I can't really read what that says down there. Okay. So what do we start with? Okay. Tan of 0 is? You guys should know this. Yeah. 0 is the answer.
That makes sense.
Was that a guess, or did you know? Okay.
Well, it's y over x.
Right? What's the graph tangent look like?
Oh.
Vertical asymptote crosses at 0, right? Those graphs help. That's why we spent so much time in pre-calculus graphing them. So I have 0 minus 0 over 0. What's that going to be?
0.
Okay. So we L'Hopital that. And the derivative tangent is?
Oh, secant squared x.
Derivative of x is 1. And derivative of, yes, thank you. Okay. All right. Let's direct substitute. What's the derivative, or I'm sorry, what's secant of 0?
0.
No.
1. Pi over 3. Yes.
It is 1. Do you see why?
What?
No.
I guess 2 and
Great.
0.
Great. So secant is 1 over cosine. What is cosine of 0? 1, right? Because the x value is 1 when the angle is 0 on the unit circle. So secant is 1 over 1. Secant squared is 1 over 1 squared, or just 1. So we have 1 minus 1 over 0.
0 over 0.
So what do we do?
L'Hopital.
Hit it again. Oh no, Mr. Kulik. Derivative of secant squared is?
Oh boy.
Secant times tan.
Cosecant.
Tan.
Negative secant.
It's 2 secant times secant times tangent.
Whoa.
How did I get that? How did I get that?
Oh, because it was, you had to do the chain rule.
Yes. What was the outer chain?
X to the
X to the second. X squared, because it was secant squared. What was the inner chain? Secant. The derivative of x squared is?
2.
2x. So that's 2 times secant. And the derivative of secant is? Secant times tangent. Now, I'm going to write that that way, Brooks.
So, I'm just curious, instead of doing the chain rule, could you do it like secant times secant?
And do a product rule instead? Yes.
Okay.
To get the same thing. Okay. What do we do next?
Plug it in.
Direct substitution. Secant of 0 is?
1.
Tangent of 0 is?
1, 0.
0 over 0.
Ugh.
Wah, wah. What do we do?
Oh, do it again?
L'Hopital again. Oh no!
Oh wait, this time it's good though.
How do you know?
Because it's gonna be x. The x is gonna go in the bottom, so just.
Yeah, so Brooks is dead on there that we know this is going to be the last step because there is no x in the denominator. What's the problem though?
I don't even know how to do the top.
The derivative of the numerator is kind of a bear, right?
Do it the same.
What I marked.
What do we have to do this?
Oh, let's get our trigger daddies.
What?
Product and then a chain inside of our product, right? So we're going to have 2 secant squared times the derivative of tangent, secant squared, times 2 tangent times the derivative of secant squared, which we know is 2 secant squared times tangent.
That's easy beat.
Oops, this should have been a plus.
My goodness.
Okay, so I have 2 secant to the 4th plus 4 secant squared tangent squared. So if I direct substitute this, secant to the fourth of 0 is
1.
1. Secant squared of 0 is
1.
tangent squared of 0 is
0. 2 over 6. It's not, it's 1/3. Oh,
What is
finally.
what is secant again? 1 over x?
1 over cosine,
Okay.
and cosine of 0 is 1. So there we go. Stunk, but we got there. Was there any way to do this? Do we have any way of hope of doing this otherwise? What else could we have done?
Change the cosine of the
Change,
whoa.
Quotient order?
Oh,
I'm
Back
not
up.
gonna talk anymore.
yeah, I think you're looking at the wrong problem, right? Yeah.
Not a quotient.
I don't know what you would have done here, to be honest with you.
oh, it was a trick question.
Yeah, I don't know that there's a good route here, unfortunately. Just kind of a stinker. Okay? So they can get ugly, but they're, if you see a polynomial in any layer, if I look at this, then I see at most 3 L'Hopitals till I'm at an answer, right? There's a polynomial down here, at most 2 L'Hopitals till an answer. You know, polynomial, at least, or at most 1 L'Hopital to an answer. But it doesn't matter. Everybody's okay? So this just made these limits quite a bit easier, right? It's now the same plan for every single one. Direct substitution. If I get an answer, I'm done. If I don't, I L'Hopital it till I do. Now I do have to check on my L'Hopitals to make sure I can't do some combining and get off the L'Hopital train, like as we saw in that third example there. But that's it. How much simpler does that make limits?
So much simpler.
Right? Instead of having like 15 different methods that you might use, we just have
Is
one.
that for thing, near, everything?
Yeah. Any indeterminate form you can do a L'Hopital to. We just didn't bother to do examples of the other types because, well, I'm over on time and I don't have.
What if it's like a non-determinate form that
Well,
needs modification, you just find the derivative?
If it's not indeterminate, then you just direct substitute and you're done. Right? There's nothing to do. If it's a different indeterminate form, you know, like 0 times infinity or infinity minus infinity or one of the exponentials, you have to do some like shoving it get it into a fraction form so you can do it, which can be tricky to varying degrees.
We don't gotta do that.
But I'm not gonna ask you to do that. I would normally ask you to do this, but we don't have time. And it's not something that AP would expect you to do, so I'm not too worried about it. I would love to have the time to do that level of coverage, but we don't this year, so we're not. I have to make some hard choices and give some stuff up every once in a while. This is me doing that. When you take Calc 1 or Calc 2 again, if you have to, maybe you don't. Good job if you didn't. You'll do this again. Probably a Calc 2 top.